this one apparently works.
This works, okay.
Yeah, but because there when
okay. So okay, this way, right?
Yeah.
No, like how?
I don't know.
No.
Put it here.
You put it here. Oh, okay. Oh, yeah. All right. Can anyone hear me? All right. All right. Good morning, everyone. So my name is Daniel Siegel, and I'm going to lecture this week on electromagnetic counterparts. So you probably heard a lot about gravitational waves and gravitational waveforms already at the school. And so my job is to talk a little bit about the electromagnetic counterparts. And since we had this fantastic event last year, this neutron star merger, GW170817, that actually showed electromagnetic counterparts across the anti-electromagnetic spectrum very spectacularly. We actually have a lot to discuss and talk about. So the basic outline for sort of this week, at least for my lectures, will be that I will try to cover as much as I can. We only have 5 lectures, and there's, of course, a wealth of material to discuss. I'll try to cover both what we call thermal transients and non-thermal transients, meaning kilonovae for the thermal part, and gamma ray burst for the non-thermal part. And I will try to sort of keep a balance between understanding some of the recent results and sort of what's going on right now in multi-messenger astronomy, but also trying to understand some of the concepts that we use there, essentially from the ground up. So to sort of really derive some of these concepts from first principles, so that we can actually understand what's going on here and what's sort of the theory behind these models. So I'll try to keep a balance between sort of deriving sort of very basic stuff on the blackboard, and then sort of accompanying this with a set of slides that will then, where we'll then try to shift gears and sort of try to make the connection to the sort of cutting edge research that is going on. So for today, I'm going to focus on kilonovae. So this morning, and also for the second lecture later this afternoon. Then tomorrow, when Sylvia will be here, we'll do a GRB session. So she will be essentially covering GRBs a little bit from the observational point of view, and I'll try to provide some theory to that, meaning that tomorrow we'll be exploring GRB central engines, so what actually powers the explosions of gamma ray bursts. And then on Wednesday and Thursday, I'll be probably talking about the afterglow modeling, so how GRBs lead to synchrotron emission, and how do we get like a broad range in frequency afterglow all the way from the radio to the X-rays from GRBs. So for today, let's focus on kilonovae. So and essentially the idea today is that we'll try to understand these recent observations of this recent kilonova that we detected, essentially from the ground up. So I'll be sort of deriving some basic theory on thermal transients that also applies more generally to broader classes of thermal transients, also supernovae type 1 or superluminous supernovae, and in particular also kilonovae. So the first lecture will essentially highlight the similarities between kilonovae and other types of thermal transients in astronomy. So how kilonovae are actually conceptually very similar to other transients that we already know for decades. And then the second lecture this afternoon will be on the kilonova microphysics, where I'll then point out how different kilonovae are from all the other transients that we know so far. So let's get started with some basic theory on thermal transients. And essentially, most of the theory that I'm going to present is actually, so you won't find any of the theory that I'm talking about this week essentially in textbooks, but some of these concepts are, you could call it classical concepts already by this time. And so what I'm going to talk about right now has essentially been developed back in the 80s, mostly by Arnett and other people. So basic transient modeling. And by transient here, I mean thermal transients, meaning modeling, basic transient modeling, meaning thermal emission that arises from some sort of astronomical explosion. So the basic setup, so the basic sort of scenario that we're going to consider is the following. So imagine we have sort of some explosion somewhere in the universe going off. And typically, most of these explosions happen on sort of very small length scales. I mean, astronomically speaking, which means sort of typically something like on the order of tens of kilometers, at least in the case of kilonovae, so that's the typical length scale sort of for neutron star mergers. And then imagine that sort of this explosion, and we are very agnostic about the actual explosion mechanism right now, so we don't care sort of what actually caused the explosion. So just to be general, so that it applies essentially to supernovae and all sorts of other transients as well. And let's imagine that sort of this explosion ejects material into space. And then let's think of this essentially as some blob of material that has been exploded. And typically, until it emits radiation so that we can actually observe it with telescopes, it has actually to undergo expansion over many orders of magnitude in length. So typical radii would be something of the order of 10 to the 15 centimeters or so. So it has to undergo many orders of magnitude in radial expansion. Let's call the total mass of this ejected material MEJ. It has some sort of inner radius Rin, and this inner innermost mass layer is moving at a velocity v naught, and let's call this outer radius essentially R out, which we can sort of think of as being essentially infinity for reasons I'll discuss in a second. And by the time that sort of this material has expanded over these many orders of times, many orders of magnitude in length, it essentially has settled down to homologous expansion. And so essentially, the radius is then simply given by some expansion velocity v, or some velocity coordinate v times the time. And this is sort of a general concept. So any sort of explosion, you can essentially show this nicely. Any sort of explosion will give rise to a spread in velocities. And as soon as you have material moving with a spread in velocities, it will always eventually sort of asymptote to homologous expansion. So this means that the sort of density profile will be a power law. So we can write the density profile as a function of r and t. So with this sort of being the radial coordinate r as some coefficient beta that we just keep as a variable over 4 pi MEJ over the inner radius at time t cubed, and then r over Rin to the power of minus beta plus 3. So this is just a power law in density that reflects this homologous expansion. And you can integrate this and convince yourself that then the mass of velocity is given. So we'll denote this in the following by just mv and just indicate that we are dealing with a velocity coordinate here. It's just given by MEJ and then a power law in velocity. So we just switched essentially variables. Instead of using r, radius, and time, we just use this sort of homology condition to sort of eliminate r and t and instead use a velocity coordinate. So now every sort of point inside this sort of shell of material now has a velocity coordinate that translates, of course, corresponds to some radius. And sort of in practice, it's actually difficult to write with this thick chalk. In practice, beta will be something. So this is for many sort of practical scenarios. This coefficient that controls this power law is usually something around 3, which means that if you look up here, the density profile goes as r to the power of -6. It's a very steep density profile, which means that essentially most of the ejected mass lies in this inner region around V0 or Rn. So this is sort of what sets the typical behavior of the transient. And this also explains why essentially we can take this r out, this outer radius, essentially to infinity, because it simply doesn't matter. The transient is always controlled essentially by the innermost part where most of the matter resides and where usually most of the heating is generated, as we'll see in a second. And that will essentially set sort of the emission characteristics of this system. Okay, let's go to the sort of basic formalism of how these systems, how such an explosion actually gives rise to electromagnetic emission. Well, essentially the evolution of this system is governed entirely, you can derive it entirely from the first law of thermodynamics. Namely, that the internal energy in a given mass layer, so this is the sort of mass layer at radius r, or equivalently at velocity coordinate v, that the change in internal energy is given by the work that this material does. In this case, the PDV work, where essentially this volume v is the volume of a thin mass shell at this radius. And sort of this PDV work needs to be done because the ejector shell is homologously expanding. So every layer has its own velocity, right? And the highest velocities are out here, and the slowest velocities are in here. So what the shell does in time is it spreads and expands over time. And this expansion is inevitable in this. This is exactly what defines this homologous phase. And if this shell undergoes this expansion, it has to do PDV work simply because this shell expands over time. So we have the PDV work done by the system, plus we may have some heating that I'll specify in a second. And we assume here that essentially there's some heating supplied by some heating source that is inside the ejector that supplies the ejector with heat. And we assume that this is thermalized, so this heating goes into internal energy. And with that being thermalized, eventually the system will radiate, will become a black body. It will radiate thermal emission by black body radiation, and that is denoted here by the luminosity. This is the radiated energy per time in black body radiation. So heating rate, this is thermal emission. And this is PDV work. Okay, in general, so just because I'll need this in a second, we can just rewrite this PDV work term as minus the internal energy divided by the radius times the radius, d radius by dt, which is simply the velocity by the definition of homologous expansion. And here we just use that we are assuming a radiation-dominated fluid, which means that the pressure is given by the internal energy divided by 3 times the volume V, and the volume, so the volume of this little shell, this thin shell at this mass coordinate here, is given by 4 pi r nu squared dr nu. And in general, the heating rate is, for most transients, sort of mainly determined by some sort of nuclear heating that comes from radioactive decays inside the ejector. I'll specify this in a second. And then we can have additional terms that, for example, come from a central engine. So some of these explosions may actually leave a neutron star remnant at the center, and this neutron star can actually put in some additional energy into the explosion. And then there can be other terms that could be fallback accretion, so maybe some of this material actually falls back on late times and then sort of gets ejected again. So there can be additional terms. So we will only focus on this radioactive heating term. In terms of, for sort of type 1 supernovae, this radioactive heating comes from the fact that these supernovae eject material that becomes fairly hot, and in this material there are alpha captures, and they form nickel-56, which is radioactive. It's a radioactive isotope, and nickel-56 decays into cobalt and then into iron, and those decays release nuclear binding energy that then becomes thermalized in the ejector, and that is actually so this radioactive energy that is heating the material at late times is exactly what produces the transients. But we'll see the transient. We'll see this in a second. For kilonovae, this nuclear heating term comes from the radioactive decay of very heavy neutron-rich nuclei that have been produced in the so-called R process, in the rapid neutron capture process that I'll be talking about in a little more detail this afternoon. So the R process, neutron captures onto seed nuclei form very heavy neutron-rich isotopes that are unstable, and they have to radioactively decay into stable isotopes. And in doing so, they release nuclear binding energy, and that is exactly what what provides the heat here. So now let's look at what is called the diffusion time for radiation in the system, because you could ask yourself, well, if we supply heating, like when and how does it actually come out of this transient? And the important quantity to look at here is the diffusion time, which I denote by TD, and this is given by essentially the distance it has to travel from sort of the radius, from the radius at where the photon is emitted. So imagine we're sitting on this mass shell and we're emitting a photon, thermal photon from here. Then it has to sort of diffuse through this sort of optically thick ejector until it finally reaches the outermost layer to be so that it can actually leak out from the system and eventually be observed by our telescopes, right? So what is the time that it takes for this photon to diffuse through the ejector to become observable? Well, this time is simply the the distance it has to travel by the light travel time. So that would be sort of the diffusion time in an optically thin system where the photon actually doesn't have to diffuse, but it just gets emitted. But now, if it's optically thick, we have to multiply this by what we call the optical depth. And we add a +1 term here just to take into account the transition to the optically thin regime when this optical depth becomes smaller than unity, which defines exactly the transition between an optically thick and an optically thin regime. Because at some point, the shell will just expand, the density will drop, and at some point, the ejector will become optically thin, and photons are just free to leave whenever they are emitted. So this +1 just accounts for the fact that we also want to be able to describe the optically thin regime. And now for homologous expansion, sort of the difference of this, sort of the thickness of this shell is always on the same order as the present radius. So this is just like a sort of crude approximation for now, but we are only interested sort of in an approximate diffusion time here. So let's do this and define sort of the first term as the diffusion time in the optically thick regime plus the light travel time, which dominates if this becomes smaller than the light travel time, okay? So, and I should also write down the definition of the optical depth. So this is something that you'll encounter everywhere in astronomy because that's really what many observers are talking all about. So this is defined as sort of the integral. And again, this outer radius, we can take this actually to infinity because for all the integrals that we're going to do, the upper bound will just not matter at all. And we can just sort of neglect the outer radius. So this is just the integral over what is called the opacity. So this is the cross-section per unit mass. So the sort of likelihood in the sense of for a photon to be captured somewhere in here, and then be forced to be re-emitted, times the density dr. And actually, this is one of the exercises for one of the sort of problem sets sessions. You can show that this is essentially given by this expression. It's essentially determined by the mass at this velocity times the opacity time divided by 4 pi the radius squared. So in other words, we find that the diffusion time, assuming that we're in the optically thick regime, is given by beta over beta plus 2, and then m nu kappa over 4 pi r nu squared c, or just to write it in a little bit more explicit terms, because we'll need this in a second, beta over beta plus 2, and then m nu over beta plus 1 over beta kappa divided by 4 pi c v naught, and then mej to the power of 1 over beta. Sorry, I forgot the time t here. So you can see that the diffusion time essentially depends on some constants, and then it scales as 1 over t. So you'll see that eventually the diffusion time will become smaller and smaller and smaller. So at some point, the material will become optically thin. And that brings us to discuss the luminosity. So for photon diffusion in such an ejector shell, the radiative flux, so this is something you can find in basic stellar astrophysics, is given essentially by the gradient of the radiation density. So that's the radiation density of photons, and that is the radiative flux. So we can now derive an expression for the luminosity, which will give us sort of this sinc term in the equation. So using this the diffusion equation here, we can write down the luminosity, which is essentially the flux multiplied by 4 pi r nu. And then we have this fraction here. So I should put these velocity coordinates in here. And we're just, so we're assuming that there's just radial flux, right? Because it's a spherical symmetric system to first order. And we'll just approximate this gradient, this derivative. So this is the energy density, U, so E divided by the volume, the internal energy divided by the volume. So we'll just assume a radial gradient, and we'll assume that this is roughly given by just EV over the volume, just divided by the radius, just to have a sort of rough scale of for this gradient. So we'll eventually end up with this expression here, 4 pi c over 3 kappa nu, and then we have E nu R nu over m v. And now if you compare this to the expression we have here, you can see that we can just re-express this in terms of the diffusion time. And now you can see the connection between the emitted luminosity and the time for photons it takes to diffuse out of the ejector. The luminosity is simply given by the internal energy at that time, at that point, divided by the time it takes to for this photon to diffuse out of the ejector. So just simply this energy over the diffusion time scale. And if you plug in all this, all this expression here, all of this expression, then you can show that very easily that this is just the energy times the time t, and then just essentially divided by constants. So beta, well, not constants, but sort of values that are simply determined locally, and that under homologous expansion don't change over time. So they are essentially just time independent. And that is a very important property, which we'll see in a second. C V naught. Okay, and then we forgot an MEJ down here, 1 over beta. So the details are not important. The only point is that it just depends on time linearly, and the rest is given by something that is time independent under homologous expansion. So in other words, yeah, and let me just say that this is the luminosity essentially in the regime as long as we are optically thick. But at some point, this time will essentially approach 0 and will not be an accurate description. So on longer time scales, we'll just use the modified diffusion time that I defined here that includes the light crossing time. So this will be just then E nu by the modified diffusion time that includes the light crossing time. All right. Now let's try to understand this equation. And so given sort of all these definitions, let's try to understand what sort of the evolution of this equation actually tells us and what we would expect from a system that behaves according to this equation. So how does the transient actually look like? So we can write this equation in terms of timescales. So you can fairly easily see that if you just divide this equation by the internal energy, we can rewrite this in the following way. And now I defined a few timescales here. The expansion timescale, the heating timescale, and the diffusion timescale. So let me write down these definitions. The expansion timescale is the radius divided by velocity. So if you see here, if we divide this term by the internal energy, and so we have simply V over R, and so the expansion timescale is just R over V, which by assuming homologous expansion is simply the time t. Then we have the heating timescale, which is simply the internal energy divided by the heating rate. So this is an energy divided by energy over time, which gives us a time scale. So this just tells us how long it takes, given a certain heating rate and a certain internal energy, to heat up that material significantly with respect to the already existing internal energy. So the important conclusion to draw from this equation is essentially that any energy that the system has is actually lost on this expansion timescale t. So any energy that has been injected on a timescale t will be lost due to adiabatic expansion on the same timescale. That means that essentially the system forgets its initial conditions fairly rapidly, simply because if you just have this explosion going on a timescale of seconds or something, which is a typical timescale for explosions, or tens of seconds, on the same timescale, essentially the material will essentially forget its initial conditions. So if you want to have a transient from that system, like a kilonova or a supernova, you actually need to heat it at late times with this heating term that provides some power at late times for the material to become hot and therefore become a black body and therefore to radiate photons. And that is also I'm not entirely sure if you followed this discussion about cocoon models and everything about the recent kilonova event. There were some claims that essentially the early blue emission that we've seen in the kilonova, so you see this first part here. So this is essentially, so this diagram here shows luminosity versus time. So this is in days. And this is sort of essentially a logarithmic measure for the luminosity, so for the emitted energy per time. And you can see that, so this is through different spectra. So this is like UV down here, and we get into the optical, and then these curves up here are actually in the near infrared. And you can see that there has been this transient peaking on a time scale in the UV. Okay, this doesn't really work well, the pointer. So you see that it peaks on fairly early time scale of a day or so. And it was argued in sort of many in many papers that this might actually come from sort of cocoon emission, which was thought to be heated ejector. So as the gamma ray burst went off in the system, it injected a jet into the a neutron star ejector, and that jet heated up this material. And it was argued that this thermal energy from this jet injection was actually responsible for the blue kilonova, but the problem is exactly that the reason why this is very unlikely is exactly this argument, because the system loses this initial energy on the same time scale that it has been injected. Essentially, so this jet was injected on a time scale of a second. So essentially, on the same time scale, you also lose that energy. So how can you have a very bright emission at one day? So on orders of magnitude larger in time on a time scale of a day. That essentially only works if you really injected probably an unphysically high amount of energy at the initial stage, simply because the system loses all this energy. Okay. So that was just a sort of side remark. And then, so the important conclusion is that ejector only generates transient if reheated at late times. And to be more specific, as we'll see in a second, this heating time scale has to be essentially comparable to the diffusion time scale. So this material has to be heated on the same time scale for this material to expand and to become optically thin. So let's see. Let's first derive another expression for this heating time scale. So in this early phase, as I mentioned, all the energy will be lost due to adiabatic expansion. So all the energy you put in at some point will be simply given by this heating term. So essentially, at early times, the internal energy, at early times, the material is optically thick, so it's very dense, still fairly compact. It loses its initial energy due to adiabatic expansion. The optical thickness will drive this diffusion time very high, so the luminosity will essentially be 0. So we lose the sink term. So the luminosity is essentially 0, simply because the optical depth is extremely high. And then if you look at this equation, essentially the energy is simply given by the integral over the heating rate. So we can just write this as sort of the integral of from Tmin to some time t over the heating rate dt. So that this heating time scale is then just approximately given by this integral over the heating rate divided by the heating rate itself. It's actually a fairly useful expression, because now we can, let me erase something. Start here. Probably keep this here for the moment. So it's also a fairly simple exercise, and that's something you can do in the hands-on sessions if you want, to show that this heating time scale is essentially also given just by the time t. And that applies to supernovae type 1, also to superluminous. And as we'll also see, it also applies to, can also derive this for kilonovae. And so for type 1 supernovae, the heating rate is given by what I mentioned earlier, by the decay of radioactive nickel. And that's simply an exponential that goes like t over the radioactive decay time scale of nickel. And as I'll show you this afternoon, for kilonovae, this heating rate at late times is given by a power law, t to the minus alpha, where alpha is roughly 1.3. So you can use these expressions and work this out yourself, and you'll find that the time scale for heating is again this time scale t. This, by the way, is actually fairly interesting because it behaves like nuclear waste that also decays with roughly the same power law. And I'll discuss this later today, like what the significance of this actually is. So now with this, so now knowing this, let's discuss when this transient peaks and how this will look like. So this is sort of the early the early phase of the transient, where essentially just acquires energy over time, because eventually this heating rate, if sort of this material actually wants to produce a transient, this heating rate has to dominate over adiabatic losses at some point. And so during this initial phase, the internal energy is simply given sort of by this integral over the heating rate. Yes? Say again? What emission? Oh, neutrino emission. Yeah, that's a good question. So neutrinos. So in order to emit neutrinos, you have to heat up the material essentially to energy scales of something like 10 MeV or so, which is the sort of weak energy scale on which you would then excite neutrino emission. For most of these transients, neutrinos may be emitted like during the explosion. So this is actually true in core collapse supernovae, and it's also true for neutron star mergers. But sort of by the time that the material has expanded into this homologous phase, the material has already cooled down quite a bit, and it's too cool actually to emit neutrinos. So neutrino emission sort of can be neglected for this context. So this is sort of the early phase of the transient. So now let's talk about the peak light, the epoch of peak light. So this is the part that we are actually interested in. So when this transient peaks, and we'll show the condition for this, which is known as Arnett's law. So you can, if you're interested, you can look up the papers by Arnett. Was derived back in '79 and in a more detailed version in '82. So that's a fairly classical result. And in order to see when and if this light curve peaks, we can simply rewrite where do I have it? With two, yeah. So we just use these two conditions. So 1 and 2. Just denote them by 1 and 2. Sort of imply that you can write this evolution equation as 1 over T times the derivative of internal energy times time, and then this is simply given then equals the heating rate minus the radiated luminosity. And now you can see from this expression here that, so note, the luminosity peaks when its derivative with time vanishes, right? Which then implies that, according to this equation, that if this vanishes from 3, because here we have exactly E times time divided by something that doesn't depend on time, that according to this equation, then the heating rate at peak light equals the luminosity. And that's exactly what's known as, so this is sort of a more general version here of what is called Arnett's law. So in other words, if we measure up here in this figure, if we sort of measure the peak luminosity of the transient, we can actually directly infer the nuclear heating rate, which is interesting because we can directly infer something about nuclear physics just by looking at the data at peak light. That's actually a very useful relation to have in mind. Now the question is, when does it actually occur? So what's actually the time scale for the luminosity to peak? Well, this is something we can easily see from this equation here. So we have these like three equivalent versions of the of the evolution equation, right? So this was the sort of basic thing we started off with. We rewrote it in terms of timescales to get an idea about the temporal evolution of the equation. And now we've sort of written this in a way that is handy in order to derive the conditions of peak light. So we can see that from this equation here. So this is the PDV term. These two vanish. So these taken together vanish. So we know that. So let's call this double star, and so we see that from this equation, it follows that the peak light so the condition for the timescale of peak light is that the diffusion timescale has to equal the heating timescale. And this is why we look so carefully at all these various timescales involved in the problem. So this is the condition for peak light. Now we know that from this little exercise that I wrote up here, that the heating timescale is actually given by the time t itself. So the actual condition, which is more familiar and is sometimes cited in papers, is actually that the diffusion timescale at peak light has to equal. So it's sort of determined by the condition that is sort of a little bit more familiar. Okay, so let's look at this conditions and see like what the actual expression for the peak timescale is. Now I can actually erase all of this. So from here it follows that the peak timescale is given beta over beta plus 2. The mass of the shell, its opacity, divided by 4 pi velocity times speed of light to the power of 1/2. So let's evaluate this term just for typical conditions for kilonovae so that we get an idea of when do we expect actually kilonovae to peak. So for kilonovae, just plugging in typical terms, say beta of 3, typical velocity of 0.1 c. So again, that is the peak timescale for any mass layer. So it still depends on this velocity coordinate v. But if we just want to get a basic idea of what the overall timescale for the whole transient is, as I said, we can simply look at this innermost mass layer because that contains most of the mass. So most of the heating is actually going on there, and that's where most of the emission will eventually come from. So just to get a basic idea about the transient in general, we can just evaluate this formula at the innermost radius, and we can derive sort of the typical peak time scale that we'd expect is 1.2 days, and then the scales as the mass, in this case MEJ, so we're just approximating that most of the mass resides at the innermost radius, so just the total in 10 to the minus 2 solar masses to the power of 1/2. We used a typical innermost velocity of 0.1, the speed of light, and then the opacity in units of 1 centimeter squared per gram to, again, to the power of 1/2. Sorry, this is minus 1/2, and this is to the power of 1/2. So for typical parameters, you can see that for kilonovae, we expect it to actually peak on a day time scale. And it also highlights immediately what kind of physics we need to understand in order to model these transients. Namely, we need to understand how much material we actually have and where does it come from. So how does it actually get ejected in neutron star mergers, something I'll discuss in the afternoon. We need to understand its velocity. So that's, again, tied to the to knowing what the actual mass ejection mechanism is in neutron star mergers. And it crucially depends on the opacity. And that's another sort of broad and big topic that I'm also going to focus on in the afternoon. Namely, depending on the composition, depending on the exact ejection mechanism, you can produce ejecta with very different composition. The R process will be qualitatively different in these cases. You could eject material that has an initial composition that only leads to sort of a weak R process in the sense that only creates fairly light elements. But you can also have mass ejection that had very neutron-rich initial conditions that would then lead to a strong R process, so produce very heavy elements. And it turns out that the opacity is orders of magnitude different for these cases. So it's really crucial to understand these initial conditions from neutron star merger simulations. And typically, the opacity can vary between 1 sort of and 100 centimeters squared per gram, where this is essentially for what we call blue emission. So this would lead to an early peak time scale of 1 day. And this is the sort of lanthanide poor case, where we only have a weak process. I'll explain this in much more detail this afternoon. And this is what we call sort of red kilonova emission, which originates from a lanthanide-rich ejecta, where a strong R process was occurring. Now, if you plug in these numbers, you can see that the peak timescales then, depending on how the composition, how the ejecta is actually, what type of ejecta we're actually looking at, the transient, so the kilonova can peak on timescales between a day and a week. And this is exactly what we've seen in this recent kilonova event, right? So we've seen one component that peaked at early times of roughly 1 day, which is exactly corresponds to this case. And we've seen this sort of more red transient that peaked on a week time scale, so 7 days. You can see this down there is actually the units in days. Peaked on a time scale of roughly 7 days, which is exactly what this formula essentially predicted. So this is just rough sort of order of magnitude estimates here, but sort of that provides the basic understanding already to much of what we can see in the data. So just as a quick summary of this transient, what we sort of expect to see is if we plot this as a function of t, and we have the radiative luminosity up here, we'll see an early phase where there's essentially sort of, this is the phase of adiabatic expansion, where essentially the luminosity is 0, the system just loses all its energy, and then at some point this heating rate will become dominant. It will dominate adiabatic expansion, and this is exactly the peak time scale, which, as we derived, is also equal to the heating time scale at that time. Sort of this is then the peak light, so the peak luminosity, and then we'll have some sort of decay phase afterwards. And many transients exactly look like this. So if you look at papers of type 1 supernovae or of superluminous supernovae, they exactly look like this. And kilonovae, in a sense, do exactly in the same way. It's just that the microphysics of these different transients differ. So finally, let's briefly discuss the spectrum. So far we were sort of only talking about what astronomers call the bolometric luminosity, so the total energy output of the system. But let's write this down essentially in terms of a frequency dependent way. So we, as I said, by writing down essentially this first law of thermodynamics, we assumed that the supplied energy is 100% thermalized. So this heating rate is thermalized, and therefore L nu, so the emitted radiation, has to be black body emission, or at least quasi sort of black body emission. Let's also note that the local gas temperature inside the ejector here is essentially given by 3 times the internal energy at that point divided by 4 pi a RV cubed. So where we assume that it's a sort of radiation-dominated gas, so for radiation-dominated gas, the energy density is simply given by A times T to the 4, where A is the radiation constant. And the point being here that the opacity depends actually on the temperature. And we'll discuss this afternoon when I'm going to talk about opacities for kilonova ejector. Now we can define the photosphere. So the photosphere of sort of a radiating astrophysical system is always defined as the point where the optical depth, as you go from infinity, you integrate over the opacity, and once the optical depth reaches unity, that's where sort of the photosphere resides. So this is where this is a characteristic sort of spherical shell in this case where photons are emitted from. So this is simply defined by that the radius, so the photospheric radius, has to. We're just writing down again the definition of the optical depth. We just integrate from infinity, so from an observer at infinity, we look into the ejector shell, into the ejector, and sort of we integrate over the opacity and density to get the optical depth. And when this optical depth reaches unity, that's what we define as the photosphere. So this again kappa r rho over r. Already written this down earlier. So when this equals unity, that is the condition for the photosphere. Now, knowing that, we can assign an effective temperature to this transient. So the effective temperature as a function of t, function of time, will simply be, okay, that need a little more space. So the effective temperature that we assign to the transient at a given time t is then given by the total luminosity that emerges from the ejector divided by 4 pi sigma and the photospheric radius squared to the power of 1/4. And you just sort of recognize this as the Stefan-Boltzmann law, right? Where the luminosity is given, if you integrate over a black body, is given by 4 pi sigma r squared and then t to the 4. So, and the total luminosity, okay, I can erase that. And the total luminosity, as I mentioned, is simply the entire radiation that is emitted from the ejector at time t. So we integrate over the whole range of radii here. And as you see, then all the internal energy at that radius is always weighted by the diffusion time. So those, so the radiation that is out here, where sort of the transient is already sort of above the photosphere, that has already sort of emitted all its internal energy. At the photosphere, this is exactly where the photons at this characteristic time are emitted from. These are still the layers that sort of lose their energy at that specific time. And interior to that, interior to the photospheric radius, material is so optically thick that the emission is suppressed by the diffusion time, which is many orders of magnitude higher than 1. So that suppresses a lot the emission. So the photosphere is really where sort of the energy comes from at that point in time. So, and then we can write down the emergent flux from this system, assuming black body radiation from this photosphere with the effective temperature that we defined. And that is simply the Planck spectrum (1 over x of h nu). So this is the frequency in contrast to the velocity. Minus 1, and then weighted by the radius by the distance. So this is the distance to observer. And sort of this then tells us what the spectrum at a given time actually looks like from this expanding shell of material. So I've now just gone through a basic sort of formalism that is applied everywhere in astronomy in order to model thermal transients. And I was just trying to highlight that kilonovae are essentially conceptually nothing sort of very specific or peculiar in this respect. They are actually simply can be described by the same formalism. The only point where kilonovae differ vastly from other astrophysical transients, other thermal astrophysical transients, is the microphysics, and this will be sort of the topic of the lecture of this afternoon. This basic model is a one-dimensional spherically symmetric model, right? And it's actually fairly easy, but it's actually fairly powerful because, as I've tried to highlight, you can get some basic understanding about transients just by analyzing some of these equations and writing down some of these timescales. And actually, if you would, and this is one potential project that if someone is interested actually to do this week, you can actually code that easily up in Python or something, type in the equations that we've derived here, and actually numerically solve this differential equation. It's just a simple sort of ordinary differential equation. You can discretize essentially just this ejector shell and then integrate it and use this black body spectrum, and then you can predict light curves in all the different wavelength bands. And the interesting thing is that this model is nice because it provides a qualitative understanding of what is going on. But even sort of on the level, on the sort of accuracy level, on the order of a factor of a few, it actually does a pretty good job. So you can actually fit some of the observations with this fairly simple model just by making crude approximations. But on the level of a factor of a few, there's many uncertainties involved here, and also how you derive sort of the ejector masses and all the fundamental parameters. So there's a lot of wiggle room, and within that you can actually gain some gain some insight from that. So if someone is interested, that's actually a fairly nice, simple project that can be done in a couple of hours or so. All right, I have until 1, right? Or I can probably start. So maybe I'll start with in the last like 7 minutes with a little bit of the microphysics discussion, just to set the stage for the second lecture this afternoon. Unless there are any questions or something on what I've covered so far. Any burning questions? Yeah. Yes, very good question. And that's exactly what we're after, right? So we do all this modeling in order to infer physical parameters from the system. So to understand what was actually going on in this, for example, in the neutron star merger that produced all this ejecta and these kind of things. And so as I mentioned already, so one fairly useful thing to know is, for example, we can constrain nuclear physics just by using this Arnett's law. If we fit a model similar to the one that I described here in the last hour or so, we can, from the peak luminosity fairly nicely constrains the heating rate, and that tells us something about the R process, about how nuclear heating is actually going on. The second thing is you can infer, so the basic parameters that you can infer is the ejecta mass. As you can see, all these equations depend on the ejecta mass. That's one fundamental parameter. What you can also infer is the characteristic expansion velocity. So and that then tells you the kinetic energy. And from the kinetic energy, you can tell like how much energy was actually there in the explosion, right? So it tells you something about the explosion energy. And from there, you can make inferences on the central engine. So you can sort of try to sort of discriminate between different models for central engines. It's simply based on energy arguments. And then it tells you, to some extent, a bit about how this velocity profile actually looks like. So you can infer essentially the slope of the density of this homologous structure to some extent. And then you can learn something about the heating rate at peak light. Although, as I'll show this afternoon, there's also uncertainties involved here. So that's something fairly useful. And then of course and from these parameters, then you get essentially all the rest. So the peak time scale, heating time scales, and these kind of things. And this is essentially what you're mostly interested in. One other parameter is sort of what goes together essentially with the heating rate is the opacity, and that tells you about the composition of the material. So with this, you can discriminate between different ejection mechanisms in neutron star mergers. So you can sort of tell, okay, this has to be maybe a tidally ejected material, or this has to come from winds from the neutron star, or this has to come from disk winds, or these kind of things. So these are fairly basic parameters, but they are in principle fairly powerful because they tell you a lot about how the ejection actually occurred and what the sort of central engine was. Okay, then let's start here. Maybe I'll keep this. Okay, so let's start part 2, kilonova microphysics. And this is where all sort of the complication comes in. Sort of the basic framework, the conceptual framework is fairly simple, but sort of this is where a lot of physics comes in. So the previous discussion essentially showed that we need to understand 3 points. So we need to understand following 3 points. The first one is we need to understand the nuclear power supply. So in order to specify this source term here. The second important point is we need to understand the opacities of our process material. And the third point is we need to understand the characteristics of ejector, meaning we need to understand how neutron star mergers give rise to mass ejection. So how much they eject, the quantity of mass. We need to understand its velocity. We need to understand the density structure. And we need to understand the initial composition, which is usually captured by a parameter that's called the electron fraction. I'll come to this. I'll discuss this in a second. And sort of thermodynamic conditions. The thermodynamic conditions for the R process. And this is why we're going to look at simulations of neutron star mergers and mass ejection later on. So let's just briefly write down 2 expressions for the heating rate, and then we'll stop because time is up. So let's start with the nuclear power supply. So, as I mentioned, just to write it down again, for kilonovae, the power supply comes from radioactive decays, and by that I mean alpha decay, beta decays, and also fission. Of heavy nuclei synthesized by the R process. And how we get those, I'll show you later this afternoon. By the R process. So, in general, this R process heating can be written as sort of the intrinsic heating rate that comes from these decays times what we call the thermalization fraction, or thermalization efficiency, so the efficiency with which the sort of decay products of the product of these decays actually lose their energy and deposit their kinetic energy in the ejector. So there's an efficiency involved here, simply because some of the decay products, such as actually neutrinos from beta decay or so, they are simply lost because they are not absorbed by the system. So that energy is entirely lost. Gamma rays are also lost, at least at late times. I'll mention this again in a second. And then the other sort of species, like electrons from beta decay or alpha particles, or actually the fission products, they actually thermalize very efficiently. But as I'll show you this afternoon, we also need to understand that in quite detail, in a lot of detail, because it can actually qualitatively also change the kilonova properties. Okay, so there's this thermalization efficiency involved, and then we need to multiply this by sorry, it's big M nu. So this is the specific heating rate. So specific R process heating rate, meaning the energy emitted per unit time per unit mass, absorbed with an efficiency eta, and then multiplied by how much R process material we actually have, the mass fraction of R process material that we have, multiplied by the total mass that we have in a sort of given shell at radius r and v. So as you can see, we need to understand two things for the R process. We need to understand how these decay products actually get thermalized and with what efficiency in the ejector, and we need to understand the intrinsic heating rate that comes, so the amount of nuclear binding energy that is released by those decays. And I'll stop here because time is up, and I'll discuss this in more detail this afternoon. Thanks. Unless there are any questions. Or we can discuss them over lunch. Yeah.
With these formulas that you did, can you normalize the light curve that you have there, just as you do for supernova 1A and get standard candles?
Yeah, that's a really good question. So kilonovae as standard candles, there are practical reasons and theoretical reasons why this is hard. The practical reasons are that we won't see kilonovae actually out to huge distances because they are intrinsically dim. So that already, sort of the name kilonova already indicates that. So a supernova is much more luminous by orders of magnitude than a kilonova. And that's how the name was actually invented in the first place. It's something in between a nova and a supernova. So it's typically actually, so there has been actually some dispute about this term, but essentially you can show that sort of a kilonova is, as the name says, like a factor of 1,000 sort of more luminous than a nova, but it is still subluminous with respect to supernovae. So these objects are intrinsically very dim, and they are in the infrared. So typically peak in the infrared if you have like heavy R process material. So this is why they are not interesting cosmologically as standard candles, simply because we won't be able to see them to far enough distances so that we would actually that we could actually use them for distances in cosmology. The rates, you mean? Yeah, the rates are much lower. So this is something I'll discuss actually in the colloquium this week. So if you look at say typical core collapse supernovae, they occur at rates much higher than kilonovae. So kilonovae are much rarer events. They are produced by neutron star mergers, and the neutron star merger rate is by orders of magnitude smaller than any of the supernova rate. Yeah. Yes.
What event more effective in producing heavy elements, kilonova or supernova?
Okay, that's also a really good question, and that will also be. I'll also discuss this actually on Wednesday in the colloquium, like what are alternative sort of sites for the production of heavy elements. So it turns out that in supernovae, in at least typical core collapse supernovae, it is very hard to produce a strong R process and therefore heavy nuclei beyond what we usually call the second or third peak of the R process. Although they have been actually, so if you go back in the literature and you read the very early papers about R process back in the 50s, it was actually speculated that supernovae would be the site to produce them, and that was sort of the leading paradigm until very recently. that's been thought that sort of in these proto when core collapse supernovae form a proto neutron star, the winds driven from this neutron star surface would actually be neutron rich enough to produce heavy R process elements. Now it turned out through a lot of theoretical studies that actually these winds reabsorb a lot of neutrinos emitted from this neutron star, and it raises the electron fraction to an extent that you can't produce the heavy R process elements anymore. And also observationally, there has been a lot of indications recently that at least the ordinary core collapse supernovae can't do the R process because the rates are actually far too high. So there's I'll discuss this in more detail in the colloquium, or we can also talk about this at more length at lunch. The upshot is simply that the ratio of how often they occur and how much material they produce is sort of in tension with some of the observational constraints we have so far. However, fairly recently, two collaborators of mine and myself, we have actually proposed a scenario in which supernovae actually can produce the R process, namely in a very rare subclass of core collapse supernovae that is known as hypernovae from the theoretical point of view, or GRB supernovae for sort of the GRB people, or almost equivalently type 1 broadline type 1 BC supernovae. And those are thought to accompany long gamma bursts. And in those systems, they are rapidly rotating. And actually, for reasons that I'll also explain in the colloquium on Wednesday, we think that those are actually the dominant contributors to the galactic R process. So that neutron star mergers are actually not the dominant source. Yeah, more on this on Wednesday. All right, then let's have lunch and reconvene this afternoon.